All right, greetings and salutations. So, last video I talked a little bit about how discrete math is uh, the mathematical framework for much of computer science. And in this video, I want to start getting into the content of what that entails. So, I'll start out today by talking a little bit about it's in eraser mode. Hold on. A little bit about propositional logic. Just the basics of propositional logic. Now, for many of us, discrete math just feels like a lot of proofs and symbol pushing without much application to computer science or programming. And I'm here to tell you that's not the case. We actually use logic quite a lot um, in coding itself, whenever we're writing if statements or while loops or for loops, we are using logic to dictate how our program flows. So before we get into how propositional logic falls into um, uh, how it applies to computer science or what it even is, I want to start out by discussing, well, what even is logic in the first place, right? We talk a lot about logic in math and computer science, but what even is logic? Well, essentially, it's the systematic study of valid reasoning and argumentation. So correct reasoning, you know, and how I like to think of it is you you have two things. You have things that you know or that you assume, right? You have information that you know, and on top of that, you have rules of inference. So you have these rules that tell you how you can use the information you know to deduce other things. So rules uh, for you have rules for reasoning about this information. Then using the information that you know and the rules for reasoning that you have, what logic discusses what new conclusions can you draw? You draw legally. What new conclusions can you legally make from the information that you know and the rules for reasoning about that information? So now that we got that out of the way, let's discuss what is a proposition. Proposition is simply a statement that is either true or false. That's all it is. Statement that is true or false. It has to be one or the other. There is no maybe. There is no half true, half false. It's either true or false. We may not know whether it's true or false, but we have to know that it is certainly either true or false. So what are let's look at some examples, right? What's one example? The the sky is blue, right? This is a statement that is we can say is either true or false. Um, Now, is it true or is it false? Well, assuming we're looking at a morning sky without many clouds, I think it's reasonable to assume that this statement is true. This proposition is true. Let's look at another one. 9 plus 10 equals 21. Is this true or false? Or is this a proposition? Yes, because it's a statement that is either true or false. Now, is it true or false? It is false because 9 plus 10 is not equal to 21. What's another example? All the unicorns in my house speak Latin. This is also something that is either true or false. And now, as counterintuitive as it seems, this statement, at least according to my knowledge, uh, I don't, I don't believe, I don't think unicorns exist. Maybe they do, but as far as I know, unicorns do not exist, and I'm pretty certain there are no unicorns in my house, and that actually makes this statement true, even though it seems like it should be false, right? Because unicorns can't speak Latin, but I'm saying all the unicorns in my house, but there are no unicorns in my house. Now we'll get later on. This is just a teaser. We'll understand why this statement is actually true later on. But the point is that it is true, which is pretty cool. Now it's another example. Um, Dolphins are fish. Now, this is a proposition. It's a statement that is either true or it's false. Now, whether it's true or false, we may never know. But the fact is that it is either true or false. Now, what about these? Let's say I have something like stop sniffing the cat. Is this a proposition? No, it's a command. There is no truth value we can assign to this. It doesn't make sense to say that this sentence is true or false. Right? It's a command. Now, what about this one? Do you know Muffin Man? The muffin. This is a question. It's not a statement, and you can't assign a truth value to it. Therefore, it's not a proposition. Now, what about one more example, non-example? The statement is false. Now, this seems like it should be a proposition because, it's a statement that when you read it out loud, it seems like you can assign a truth value to it, like this statement is true or it's false. But think about it. It's actually a paradox. There is no truth value we can assign to this because no matter what we pick, true or false, it can never be either of those. Suppose that this proposition, suppose say this sentence is true, right? If the sentence is true, then this statement, but it says this statement is false. So if it's true, then it should be false, which doesn't make sense. Say that it was false. This statement is false, but then that makes this statement true. I know it's trippy. It sounds really weird and it kind of hurts your head to think about, but really think about it and understand why you can't say whether this is true or false, and therefore it can't be a proposition. Now, we use propositions all the time in programming. So, like I said, whenever we write our if statements or while loops, we're using propositions to control the behavior of how they execute or if they execute. Think Boolean expressions. If you want to think about what a proposition is, think Boolean expression, something that evaluates to either true or false. So if you want to, so if you have a code snippet saying if if x is, let's start with pseudocode. If x is even, then do something. If x is even, do something. Well, this x is even condition, that would be our proposition. That would be our Boolean expression. This would evaluate to either true or false. Now, of course, in code, we wouldn't write x is even. We would write if something like x modulo 2 equals 0. This is how we would say if x is even in code speak. But this is basically propositional logic at work right here. You know, assuming that this x variable is, there is a value assigned to x. Otherwise, this statement wouldn't make sense. You can't have just a variable without. I mean, you can have variables. We'll get into statements with variables later, but in general, you shouldn't have variables in propositions. So x should have a concrete value. But in Boolean expressions, you know, that's just the analog for propositions. Anyway, that's getting too deep. Not right now. So yeah, that's how we use propositions in code. Now we have these very simple propositions, but how do we make even more complex propositions? Like say we want to say, say that we have a proposition P. So in math, we don't always, when we're reasoning about propositions, we don't always want to write out the sentences word for word explicitly. We don't want to write out the statements. So we'll often just assign letters to represent them. So we'll let P be the proposition. Bob has homework. That's the proposition P. So whenever we say P, we're really just saying Bob has homework. And we can let Q be the proposition Bob has an exam. Now, suppose we want to make more complex propositions like, Bob has homework and an exam. Or Bob does not have a homework. Well, we can actually do that using these things that we have in propositional logic called logical connectives. Logical connectives, right? So what are these? Well, there are, first there are three main ones that I want to talk about, right? So there is not. This means not P, right? This little sideways L-shaped thing means not P. Read it as not P. Now, suppose that P is true. Say that P is a true proposition. Then not P would be true exactly when P is false. So this creates a new proposition right here. Adding this connective to P makes this a whole new proposition on its own. P is a proposition, and now not P is also a proposition. So if P is true, then not P is false. If P is false, then not P is true. And we can actually make that explicit by using a truth table. A truth table is basically just a systematic way of simulating all the possibilities for the truth values of propositions. So we have the proposition P, and what are all the truth values that P could take? Well, P could be either true or false. That's it, right? There is no in between. It can either be true or false. So what is not P? When P is true, then not P should be not true, which is false. When P is false, then not P would be true. So this is our truth table for not connected. So if P is Bob has homework, not P is Bob does not have homework. Or not Bob has homework. Now the next connective I want to talk about is and. So say that we want to say Bob has homework and Bob has an exam. It's P and this upside down B-shaped character, Q. This reads as P and Q. And the truth table for this is, well, let's see, what you have P and what are all the basic propositions we have? We have P, we have Q, and we also have P and Q. Right. So what are all the truth values that P could take? Well, just true or false, right? But we also have Q, which makes this a little bit more complex because now we're not only looking at the combinations of truth values just for P, but also for Q, because Q is a whole new atomic or basic proposition on its own. So what are all the combinations of truth values we could have for P and Q combined? Well, we could have P is true and Q is true. We could have P is false and Q is true, right? P is true, Q is true. P is false and Q is true. We could have P is true and Q is false. We could have P is false and Q is true. These are the four possible combinations we can have. True, true, false, true, true, false, false, true. So now that's how we simulate all the possible combinations of truth value in our truth table right here. And what this P and Q means is this is how it's defined. P and Q, this statement P and Q is true exactly when both P is true and Q is true, which is only this first row right here. So P and Q is defined to be true exactly when P is true and Q is true. If either one of these is false, oh wait, this should be false, my bad. Made a mistake over here. This should be false. True, true, false, true, true, false, false, false. So P and Q is true exactly when both are true. So this has false, true. Oh, there's a false. So P and Q is false. It's true, false. P and Q is false. Both of these are false, so P and Q is false. So the only way P and Q is true is when both of these are true. Now we have our third logical connective we will talk about is or. So say that we want to say Bob has homework or an exam, or both. That's the funny thing about the word or in math. So we write this not upside down B character for or, and we read this as P or Q. Now, how we define this P or Q is, it's a little bit different than in English. In English, we can say, if we say, oh, this ball is blue or red, we take it to mean that it is either blue or red, but not both. However, in math, it's different. So we'll see that here. We have our truth table, construct a truth table. So we have P and Q for our basic atomic propositions, and then we have P or Q right here. And what are all the combinations? Well, if true, 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 false, false, true, false, false. So P or Q, the statement P or Q is defined to be true if at least one of P is true or Q is true, or both, right? At least one of them has to be true. So in this case, P is true and Q is true. Okay, that works. One of them is true, so that works. In the second row, P is true, Q is false, but P is still true, so this is true. In the third row, Q is true, so the statement is true. In the last row, neither P nor Q are true, and that's when this statement is false. So this is how P or Q is defined. Now let's look at some examples of how these statements could be used in programming. So say that suppose we have a person object Bob, right? We want to write if I'll use like more Java C syntax here and there, or maybe like Python. I'm not sure what sort of syntax I'll use for the pseudocode. I'll just wing this, or I'll make it up as I go. But it's not doesn't matter too much as long as the basic idea is communicated. But so I can say if not Bob dot has homework. Maybe this has homework is a Boolean function that returns what true if Bob has homework, or and false if Bob does not have homework. So if not Bob has homework, then say Bob dot party. Bob goes to party because he doesn't have homework. He's chilling. Suppose Bob has homework or Bob has an exam. And note that this or operator is exactly how it works in programming as well. In your code, the or works as either this is true, either Bob has homework is true, or Bob has exam is true, or both are true. So it's the way it's defined in math is exactly the same way as this or operator is defined in at least programming languages like C and Java or Python. Right? So we can say if Bob has homework or Bob has exam, which means if Bob has homework or Bob has an exam, P or Q, or both, right? If Bob has both, then we can say Bob go to library. Go to library to lock in and do his work, because Bob can't party tonight because Bob has stuff to do. Either has to do his homework or study for exam or something. Now, suppose that Bob has homework and Bob has an exam, right? That's a special case of this previous statement. So if Bob has homework and Bob has an exam, this if statement would if statement right here would still trigger. It would still enter this if statement, and Bob would go to the library. Now, so if Bob has homework and Bob has an exam, well, Bob will have already gone to the library because that this condition, this Boolean condition right here meets this Boolean condition right here. It's a special case of that. This is P and Q. Now Bob will go to the library, and then we can say, all right, then Bob goes to the library, then he gets overwhelmed. Bob gets overwhelmed because he has too much work to do. He has both homework and an exam. He's like, ah, man, I have so much stuff to do, and I'm just so he gets overwhelmed, and then he goes to party instead. He skips all his work altogether and decides to go party. So that's what happens when Bob has both homework and an exam. Those are some examples on how you can use logical connectives in your code. Now, those were the three basic logical connectives I want to talk about first. There are a couple more I'm going to get into now. This next one, it's a special one. It's so this logical connective is called implication. This is implication. We read this as P. Sorry, actually, wait. I'll write like this. We read this as if P, then Q. Another way you could say that is P implies Q. You could also say, you could also say P is sufficient for Q, P only if Q. There are different ways to say it, but these are the two main ways that you'll usually hear this read, at least from my experience. And this logical connective is saying whenever P, so this statement, this compound logical statement right here is, we can again make a truth table to define when exactly it's true. So we'll make a truth table. We have P, Q, and P arrow Q, or P implies Q. Right? Now, again, just like in the and or, we have the four combinations: true, 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 false, false, true, false, false. The way we define P implies Q is we say that this statement is true exactly when, how do I say this? Whenever P is true, then Q must be true. If whenever P is true, Q is also true, then this entire statement is true. And I'll explain what that means in just a minute. So in this case, whenever P is true, P is true in this first row, then Q is also true. So we say this is true. Whenever P is Q, Q must be true. Now P is true in the second row, but Q is false, which means this statement is false. Now, whenever P is true, Q must be true. So in the third row, well, P is false. P is not true. So, and that's the same in the fourth row. So when P is false, we actually don't care whether Q is true or false. We only care if Q is true whenever P is true. So if P is false, we don't care, and we can say these two are true. So I know this is confusing. When I first learned about it, I was pretty tripped up on it for quite a bit, for quite a while. And the way my teacher taught the way my teacher taught me this implication statement, P implies Q, that I thought was a really neat way of putting it is think about it as as keeping your promise or breaking your promise, right? So this P implies Q statement is false exactly when you break your promise. And I'll explain what that means right now. So say that say that Kim and Sally are siblings, right? Kim is the older sister, and then Sally is the younger sibling. And you know how younger siblings are. Well, you know how older siblings are. They'll start something for no reason, bully their younger sibling, and the younger sibling will do just about anything to get their older sibling in trouble. Right? That's just how siblings work, right? So say that Sally says to Kim. So Sally says to Kim, and Kim is being a menace. Kim keeps coming over while Sally is watching TV and taking the remote and turning off the TV while she's watching. So Sally says to Kim, if uh, if you turn off the TV, then I will scream to get Kim in trouble. So Sally says to Kim, if you turn off the TV, then I will scream. That's her promise. She's promising to scream if Kim turns off the TV. So suppose that we have a you make P the proposition Kim turns off the TV. And we make Q the proposition Sally screams. Now, what are all the different cases that could happen? Well, let's if we go up to our truth table right here, we have 4 different combinations, right? So we can have this is the true case. Kim turns off the TV, and then Q is so this is P, and this is Q. Right? And this is P implies Q. So Kim turns off the TV, and Sally screams. Just like Sally promised she would do. Kim turned off the TV and Sally screamed. So Sally did not break her promise, so this implication statement is true. It's the second case. True, false. Okay. So in the second case, Kim turns off the TV and Sally does not scream. Wow. Maybe Sally is feeling a bit nice that day, or maybe Kim's just giving her a little mean look saying, Sally, if you scream, I don't know, man, something's gonna happen, something's gonna go down. Maybe Sally's scared, who knows? So Sally does not scream. Well, she still broke her promise. Sally promised to scream if Kim turned off the TV, and Sally did not scream, right? She broke her promise. So that would make this implication statement false. Suppose that Kim does not turn off the TV, and then Sally screams. Oh, Sally didn't break her promise. She said she will scream if Kim turns off the TV. But Kim didn't turn off the TV, so it doesn't matter. Sally just screamed. Sally screamed, but it has nothing to do with the promise she made before, because the promise, she promised to scream if Kim turned off the TV. If she doesn't turn off the TV, then who cares? That promise doesn't really uh, apply. So she didn't break her promise, which makes this statement true. Similarly, in the last case, Kim does not turn off the TV, and Sally does not scream. Maybe they started to get along. I don't know. So Sally still didn't break her promise, which makes this statement true. So think P implies Q is false only when the promise is broken. You can think of P as the P is the condition on which if that is met, then Q must not be broken. Whenever P is true, Q must be true. So that's implication. And you can use that in code the way it shows up in code. Suppose you want to reason about code actually. Yeah. Say that this shows up in code in reasoning about the code that you write. So say that you have this function, right? You have a function that returns an integer and you call it return return first number, and you take in array, right? You have a function that returns. So this array is an integer array, and you just return. It's a very simple function. You return the first element of the array. So array 0. And that's all you're doing. It's a very, very simple function. And let's, just to make this simple, let's assume that the array's size is greater than 0. So let's just assume that whatever array is passed, the arrays has to have at least one element in it. So it's an integer array and just returns the first element. Now, we can make a statement about this function saying if array is sorted lowest to highest, so if the integers are in ascending order or non-decreasing order, so if the array pass is sorted lowest to highest, then the element returned is the smallest number in the array, the least number in the array. So we're saying if this array right here is sorted non-decreasing, so it's going from smallest number to biggest number, then this return array 0 will return the smallest number. So in this case, this array is sorted lowest to highest, that would be P. Then the element returns the smallest, that would be Q. We're saying if P, then Q. And it's clear why this statement is true, right? Because if the array is sorted, if it's sorted, then the lowest element, the smallest element, should be in the first position. And this return statement returns the element in the first position. So this statement, whenever P is true, Q must be true. Now, let's look at if P is false. Suppose that the array is not sorted. Well, then there's no guarantee. We can't guarantee that the element returned is the smallest. It could be, but it may not be. So it doesn't matter if suppose that P is false, suppose that the array is not sorted. Then this statement Q, whether the element returns the smallest, it could be true, it could be false, but it doesn't matter. This statement is still, it will still hold true. Now let's look at a case where P is false, but Q returns, Q not returns, Q is still true. So say that we pass in, or Q is false. So suppose P is false and Q is false. Maybe that's because we passed in an array like 2, 1, 3, 6, 8, right? So the function will return the first element, which is 2. And that is clearly not the smallest is 1. Suppose we pass in an array like 1, 3, 8, 4, 3. Well, now it just happens to be that the first element is the smallest. And so this is a case where this is a case where P is false and Q is false. This is a situation where P is false, but Q is true. But either way, it doesn't matter. We're only concerned the truth value of this statement only really matters, or it's determined only when if P is true. If P is not true, it doesn't matter. The statement will always be true. As long as P is true, we must ensure that Q is true, which it does, because if the array is sorted, then this function will return the smallest element. Q will be true. So that's an example of how implication works. Now this video is already quite long, so I'm gonna stop here. But in the next part, I will continue more on. I'll give another example on compound propositions as well as something called a biconditional statement, which is, so this is called a conditional. This is implication. You can call it conditional, a biconditional. We'll get into that the next video. So anyway, thank you for watching. Stop recording. Let's see. Okay.